Good morning, everyone. I'm Ben. I'm a postdoc currently at Brown, and I want to tell you about some work we've been doing here on understanding misconceptions with LTL. And LTL stands for Linear Temporal Logic. So this talk was originally given at VardiFest, a celebration of Moshe Vardi's great work on LTL and many other topics and formal methods and programming languages. And that was earlier today, August 1st. Took place in Israel, but I'm here remotely from Smyrna, Delaware. Okay, so let's get started. Mistakes in LTL. So we've been doing user studies for the past over 2 years now. We want to understand specifically in what ways do users have trouble expressing thoughts using an LTL formula? And once we know about these misconceptions, what can we do to correct for them and have more reliable formulas going forward? And we've been studying these questions with a variety of populations, including students and researchers who use LTL in their work. And we've been using a variety of methods. So both surveys, talk-aloud interviews, several others. And the goal of using so many methods of populations is to make sure that we've got a grip on misconceptions as opposed to mistakes. Because if there's a survey response that's incorrect, it could be incorrect for a variety of reasons. So we need to make sure that we get the rationale behind the answer to know that there's really a misconception at play or not. So now I would like to tell you about the results, but I'm going to do it by showing you, and we'll have a little quiz format. Oh man. Quiz with lots of yes and no questions. So let's get started. Part 1 is comparing LTL formulas to traces of a system with 3 lights in it. So question, do the traces below, which will appear in a minute, do they satisfy this formula, eventually red and eventually green? So here's the first trace. It's got 5 states of our 3-light system. 5 states are shown, but really it's an infinite trace because the 5th state will repeat forever. In the first state, the red light is on and no other lights are on. In the second state, no lights are on. In the third state, the blue light is on and no other lights. In the 4th state, nothing. And in the 5th, and every state after that, red is on. So does this satisfy our formula, eventually red and eventually green? Yes or no? The answer is no, and that's because green is never on. Here's another trace now. We've got nothing for the first 3 states, then all 3 lights, red, green, blue, in state 4, nothing after that. Does this satisfy the formula? Yes or no? Yes, and that's because both red and green turn on in that 4th state. One more, we've got nothing in first, green only in second, nothing in third, nothing in 4th, and red for everything after that. Yes or no? Yes, because both green and red turn on at some point. So I want to zoom in on this 3rd trace. So one interesting set of responses that's come out of our studies has been, this trace does not satisfy the formula. That's incorrect, but it doesn't, and the rationale is because green comes before red, but in the formula, red comes first. So we call this a bad prop misconception because we've got a standard propositional logic operator, and now it's being misunderstood to have a sort of temporal meaning, or order suddenly matters with and. So that's interesting. Here's another question. Consider the formula red. And now here's a trace. No lights in none of the states. Does this satisfy the formula red? Yes or no? No. There's no red, so no. Here's another trace. Red in state 1, nothing, state 2, and then red again in 3 and in 5 and after that. Does this satisfy? Yes or no? Yes, because red is on in that first state. And now one more, green and blue in state 1, and then red, green, blue in all the other states. Yes or no? No. And that's because state 1 does not have red, and that's exactly what the formula is asking for. And yet, we've seen many, many responses. It's usually more than half, especially when we talk to the students that we've had. This trace does satisfy the formula, and the reasoning is because red is on at some point. So this points to an implicit F misconception, thinking that a formula like red that doesn't have any temporal operators around it should be interpreted as having an implicit eventually, or implicit F on the outside of it. We also see implicit always, although I don't have a question to illustrate that one for you too. But how do you interpret a formula with no quantifiers? And there's a variety of errors that show up with that. Now, a third and last trace question, we have to get to until at some point. Red until blue is our formula. So this until is strong until, just to be clear. Here's the first trace. Now, does this trace where red is on in every state satisfy red until blue? Yes or no? No. And that's because we need blue to come on at some point for strong until. Now, another trace, red, 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 and then blue after that. Does this satisfy red until blue? Yes or no? Yes. And a third one, blue is on in state one, and then nothing is on after that. Does this satisfy? Yes or no? Yes, because we don't need any reds as long as red is true for every state before blue comes true. So if blue is on in the first state, we are okay. Zoom in on the first one. We've seen lots of responses that say this trace does satisfy the formula. And that points to a mix-up between strong until and weak until. And we've been very surprised to see this mix-up even among researchers who use LTL in their work. There's something going on here. My thought is it's a vernacular misconception with programming languages. Some languages have until loops, and many languages have while loops. And both of these, while and until, are the weak version, not the strong version. So I think just reading until, and unless you think very carefully about it, or you're very tuned up on LTL semantics, it's easy to slip into the weak until. Now let's go to part 2 questions, translating LTL to English. Here's a first LTL formula to translate: red until blue and always red. So I'll give you a minute to think about how to translate this one to English. And now let me show you one potential translation. Red is always on. So is that a correct translation? Yes or no? No, it's not. It's not strong enough. Here's another translation. Red is always on and blue is eventually on. Yes or no? Yes, this one is strong enough. We've got both parts that we need. Now here's a third possibility. This statement can never be satisfied. Yes or no? And that's a no, because we just saw a satisfying translation. This third one, though, is interesting because it points to what we call an exclusive U misconception. It says, in this case, we've got red until blue, so that must mean when blue turns on, red has to turn off. So the exclusivity in general is saying that when the right-hand side of an until is satisfied, the left-hand side has to be false. These two things have to happen at the same time. And that's not right. So we label that as an important misconception to know of. Here's one other translation question. Formula, eventually red implies always blue. So let's look at a couple possible translations. If red is ever on, then blue is always on. Is that correct translation? Yes or no? That is a yes. That one's correct. Here's another. Red is on at some point, after which blue is on. Is that correct? Yes or no? No, it is incorrect. But this is one that we've seen in the responses, and it's interesting in a few ways, one of which is it suggests that red must turn on at some point. In the formula, we've got a standard implication there, and this is just implication from propositional logic. There's no guarantee that the left part, the premise of the implication, will be satisfied. But the English response down below suggests that it has to be. So this one falls under bad prop misconception. Okay, and that's good for part 2. That gives you a sample of what we've been doing. Now, let me show you one example, part 3 question, translating English to LTL. And there's only one example because these are tougher questions. Translate this sentence to LTL. The red light is on in exactly one state, but not necessarily the first state. Here's one possible translation. Impossible. This can't be translated. LTL can't express exactly one state. So is that correct or not? Yes or no? No. We can translate it. So here's another shot. Eventually red and always, red implies always not red. Is this a correct translation? Yes or no? No. It is close, but not quite right. So here's a twist on that last one. Eventually red and always, red implies after, always not red. And that after is the key. This final one is correct, and the middle one is not. And the issue is that, again, we've just got a standard implication with that arrow. Implication means the current state. And if you want to talk about the next state, you have to add the LTL operator after. So we're pointing at the wrong state index otherwise. So well done. We finished the quiz together. How did it go? So for the VardiFest audience, I figured there would be 2 main populations here. For many people, I hope, yes, I understand these formulas are tricky in subtle ways, and it's surprisingly tricky in some cases. These questions are not so easy as they might seem at first. But there are also some masters in the world. And the danger, though, is if the LTL master thinks that all of these are obvious and the issues that arise are not significant, because we have lots of responses and from lots of well-informed people that are getting the answers not quite right, especially for that last one, the translation. Going from English to LTL, it's definitely tricky. So we need to be aware of these and watch out for expert blind spots. It's not all obvious, but we need to know exactly how it's not obvious. What's the problem? The quiz questions that I've shown have been adapted from 3 test instruments that we've developed. And the 3 instruments correspond to the 3 question parts, 3 question types that I mentioned. Translations, back and forth from English to LTL, and the trace satisfaction questions. And these instruments are all available to use. To analyze responses, we've developed a code book. And currently we have 8 codes in the book, and these are names that we've seen before on the slides. And so this is also free to use, so that if you deploy the instruments, you can analyze the results in a quick fashion. So where do we go from here? Now we have some sense of LTL misconceptions. What's next? Wait. First, of course, is to teach better. Now that we know about these issues, teach about them. Make sure that students in a class learning LTL do a better job. And our instruments can certainly help with this. Deploy them, see what the responses are, and talk about them. It's important to remember, though, that people are learning LTL not just in the classroom. There's a huge and growing interest among companies to deploy LTL and other formal logics to make sure that we have software that works exactly as it's intended, or if not software, a model of the software. So bottom line, LTL learners are all over. They don't all have the luxury of attending a semester course, and they might not have training in formal logic. So it's worth going further. Beyond the teaching, what else can we do? So one is to use the insights that we've gotten when building tools. So if there's a tool that's going to help with the authoring of an LTL formula, that tool should have some fail-safes, some safeguards to make sure that make sure that the author of the formula is aware of these pitfalls. And then the author can decide whether or not the formula that they've written is correct. It would be good to show consequences of a formula, maybe subtle traces that are allowed. And now you as the author can decide, oh, do I want to allow that behavior? Or is that something that I should go back, refine my formula, and find a way to rule out? And then path 3 is to use these results in the design of new temporal logics. And I want to point out alloy 6, which has incorporated the electrum syntax for LTL. So our findings so far have inspired 2 changes to alloy 6 and electrum based on these vernacular issues that we found. So 3 paths to explore going forward: teach better, build tools, design logics, and of course we can use more user studies to find more misconceptions. And with that, that's the end of this short talk. So thank you for listening, and I would be happy to talk more about this offline. Just send me an email. And with that, Ben and Ellis will say goodbye. You might just go to sleep again after this. I hope so. Bye-bye. Bye-bye.